Hi everyone, my name is Soruri Ponchalanwa. I'm proud to present this work, Testing Dafny, which is part of my internship at AWS last year, to increase confidence that tools that we use are correct. Without further ado, let's get started. We all know program correctness is important. Let's say that we want to write a program that converts a bit to a boolean in JavaScript. That is to say, it should convert 0 to false and 1 to true. Here's a program, except that, oops, I made a typo. So the program is in fact incorrect. What can we do to prevent this kind of mistake? Well, we could use a verification toolchain like Dafny. We write this very same function in the Dafny language, which allows us to put annotations on the program in the same style for the Floyd Hall logic. The annotation might be precondition or postcondition, and this provides a specification for the function. The annotations could also be assertions, and these are to guide the Dafny verifier to prove that our program satisfies the specification. In this case, obviously, our program does not satisfy the specification, and the Dafny verifier rightfully flags the problem, indicating that the assertion might not hold. After we correct the mistake, Dafny certifies that our program is verified. But that's not what we want though, right? Remember that we want a JavaScript function that converts a bit to a boolean, not a Dafny function, which is not executable in the environment that we want. Fortunately, the Dafny verification toolchain comes with a Dafny to JavaScript compiler, and it would compile our Dafny program that satisfies the specification to a semantically equivalent program in JavaScript. And this is it. This is what we want. Now, let's think about it. What could go wrong is pipeline. One possible issue is that the verifier might not be sound. That is to say, we have a program that does not satisfy the given specification, but Dafny erroneously indicates that the program is verified anyway. Hence, the compiled program is incorrect. Another is precision issue. We might be doing everything correct. The program satisfies the specification, but Dafny is unable to verify it. Now, to be clear, verifiers like Dafny are imprecise by design. That is why it has the assertion statement to guide the verifier to prove non-obvious specifications in the first place. However, it's still true that precision issues affect the usability of tools, and we would like to flag these issues. Lastly, there could be compilers issues. The Dafny program that we write truly satisfies the specification, and the Dafny verifier is able to prove it. Unfortunately, in this scenario, the compiler is faulty, making the resulting program not semantically equivalent to the original Dafny program. So what can we do? How can we be confident that the Dafny verification toolchain doesn't have all these issues in the pipeline? And if not, how can we discover these issues? One possibility is to do formal verification for the verification toolchain. It's certainly possible, but that takes a lot of effort to do so. Let's just focus on the compilation process. The ComCert project is a good example to demonstrate that it takes several years to do this kind of formal verification. And while our compilation process may be easier to verify compared to ComCert, we have many Dafny compilers: Go, Java, JavaScript, C#, and if I recall correctly, C++, Python, and Rust are recently added as well. So we really cannot afford to do formal verification in our case. And this shapes our design decision to do lightweight random testing instead. What about the verifier? At ISTA 2019, there is a work that employs differential testing for program analyzers. Can we adopt that approach for Dafny? Unfortunately, Dafny has only one verifier, so we cannot use a verifier as a ground truth to test another verifier. Testing verifier presents a technical challenge in our work, and we develop an annotation generation procedure based on concrete execution to address this challenge. I will talk more about what this exactly means in the next couple of slides. So, our contributions are as follows. we implement the testing framework that we call XDSmith. It targets the whole Dafny toolchain, both verification and compilation. The tool is now open source and available publicly. We developed the aforementioned annotation generation procedure to randomly test Floyd Hall style verifiers. And finally, we present an evaluation to demonstrate the effectiveness of our system. Here's an overview of the XDSmith system. The system starts by generating an X-Dafny program, which is a subset of Dafny programs, and an expectation, which could be either there is a specification violation or there is no specification violation. Given this, we can run the X-Dafny program through the Dafny verifier, and there are three possible outcomes. If the verification result doesn't match up with the expectation, we find a bug. Otherwise, the verification result matches up with the expectation. In case that the program is not verified, we cannot do anything further, so we start the testing loop again. Otherwise, the program is verified, so we can use it for compiler differential testing. Let's now focus on the initial part of the system, program test generation. It consists of three subcomponents: basic test generator, a transformer, and an annotation generator. Say that we want to test for precision issues. The high-level plan of attack is as follows. We will generate an annotated X-Dafny program that has no specification violation and give it to the verifier. If the verifier cannot verify the program, then we discover a precision issue. Now, how can we generate an annotation such that there is no specification violation? Well, what we can do is that we can run the program concretely to obtain the concrete execution trace. The trace becomes a ground truth that is used as a basis for generating annotations. The process starts with the basic test generator, which generates a well-formed X-Dafny program without any annotation. A characteristic of an X-Dafny program is that it utilizes the print statement, which is crucial for both annotation generation and differential testing for the compilers. We put some restrictions in the X-Dafny program so that it is easy for us to satisfy the Dafny verifier. For instance, we do not add any looping constructs because doing so would require us to provide a proof of termination. Given this initial X-Dafny program, we transform the program to unroll it so that each function is called at most once and log the inputs and outputs of the functions. By running this transform program, we obtain a concrete execution trace. Next, the annotation generator takes in the transform program and the concrete trace and produce an X-Dafny program with annotations that have no specification violation. Annotations at the function boundaries must be precise to help with modular verification, but annotations elsewhere can be less precise. Now, how are these annotations synthesized? By using this Rosette solver-aided language to perform example-based program synthesis. And that's it. This is how we obtain annotated X-Dafny program suitable for finding precision issues. Attempting to discover soundness issues follows the same procedure, except that we want the annotated program to have at least one specification violation. This is so that if the verifier erroneously verifies it, we will discover a soundness issue. How do we generate the annotations? Again, by using the Rosette to do the heavy lifting. Now, given an X-Dafny program with no specification violation, we could perform the conceptually straightforward differential testing. We provide a program to multiple compilers, run the compiled programs, and see if their outputs are the same. The difficulty here is in the underspecified behaviors of many constructs in Dafny, which allows different compilers to produce programs with different behaviors, causing legal mismatches in the outputs. It is a job of the Oracle to normalize the outputs so that XDSmith doesn't report legal mismatches as illegal mismatches. Now, there's one component that I skip over, which is the very first component, the basic test generator. The generator produces a random, well-formed X-Dafny program without any annotation. And this is done by using a research tool named XDSmith, which provides a domain-specific language to create a program generator. Let's now move to the final section, which is the results. We ran our XDSmith system on AWS batch. We discovered 31 issues in total across the verification toolchain pipeline with different testing methods that we devised. Some of these issues are already fixed. Let me present some of the highlighted issues. This one is a bug in every compiler except Java. Dafny supports a data type multiset, and it further supports setting the multiplicity of an element. So what will happen if we set multiplicity to 0? Well, the element is effectively removed. Many compilers' runtime libraries are unable to handle this corner case, causing the 4 compiled programs to all behave differently. This one is also a bug in the compiler. Dafny supports the superset operation. Obviously, empty set is not a superset of a singleton set, but all compiled programs produce true. This bug is in the common simplifier shared by every compiler. That means differential testing for compiler issues would never discover the issue. This is what makes it very interesting. The bug is in fact discovered by verifier testing for precision issues. By turning printed expression, which is true according to the concrete execution trace, to an assertion, the verifier is unable to verify it. It turns out that here, the verifier is right, and all compilers are wrong. To sum up, XDSmith is a framework for random testing for the Dafny verification toolchain. It tests both verification and compilation using various techniques, and we demonstrated that it is effective for finding bugs in the verification toolchain. The framework is publicly available as shown on the screen. Thank you for listening.